Hello students, I am Professor Mangesh Jamdhade, Department of Physics, S.V.K.T College, Devlali Camp. We are studying the course of Atomic and Molecular Physics. In the previous lecture, we have studied about the quantum numbers, in which we have covered the principal quantum number, orbital quantum number, magnetic orbital quantum number, spin quantum number, magnetic spin quantum number, and total angular momentum quantum numbers. And also we have seen how to draw the vector diagrams for the orbital angular momentum vector using the value of the angular momentum quantum number. And also in the previous lecture we seen that the spin of the electron has only two values, either up spin corresponding to +1/2 and the down spin corresponding to -1/2. Now in today's lecture we are going to study about the Pauli's exclusion principle. Also in this lecture we will study about the Hund's rule. Also we will study how to write the electronic configuration for the particular atom. And also we will write the quantum state of an electron. So today's learning objectives will be to understand the Pauli's exclusion principle and to understand the Hund's rule and electronic configuration of the atom. Now let's start with the Pauli's exclusion principle. The statement of the Pauli's exclusion principle is as follows. The Pauli's exclusion principle states that no two electrons in the same atom can have a same set of all four quantum numbers. So according to this principle, each electron in an atom have a different values of this set of four quantum numbers n, l, ml and ms, so that the at least one quantum number out of these four quantum numbers, any one should be different for every electron. So no two electron can have a same values of n, l, ml and ms. So thus this Pauli's exclusion principle puts certain restrictions on the values of four quantum numbers. So what values should the four quantum numbers take? There is some restriction on that kept by this Pauli's exclusion principle. So for example, if you take a principal quantum number n, now we already know that principal quantum number n takes a value from 1 and it quantizes the radius of the orbit and energy of the orbit. So in any orbit there can be no more than 2n square electron. So for the given value of n, the number of electrons in the orbit are 2n square. For example, for n equals to 2, I will get 2n square equals to 8. That is, in orbit number 2 we will have only 8 electrons. We cannot have more than 8 electrons. And for the given value of L, that is for given orbital angular momentum quantum number, there can be only 2 into 2L plus 1 electrons in that orbital. So for example, if I take L equals to 1, then I will get 2 into 2L plus 1 as 6. So for L equal to 1, we can only have 6 electrons in that orbital. Now consider here case n equal to 1. Now according to Pauli's exclusion principle, we should have the different values for n, l, ml and ms. Now for n equals to 1, we can have 2n square electrons in that orbit. So for n equal to 1, we will have only 2 electrons. So let's consider here for the first electron, you can observe that column wise for the first electron, n value is 1, l value is 0 because l is always less than 1. L is starting from 0 up to n minus 1. So here n is 1, so L will be 0 only. So L is 0, ml is also 0. We also know how to write the values of ml. ml starts from minus L to plus L including 0. So ml will be 0, and for the first electron the magnetic spin quantum number will be +12. So electron have a spin s equal to half and ms has a two value, plus half and minus half. So for first electron we will have ms equal to plus half. So for the first electron you can observe that here we have the value of n as a 1, value of l as a 0, value of ml as a 0, and value of ms as a plus half. Similarly for the second electron in the first orbit, that is n equal to 1, the second electron has a n equal to 1, l equal to 0, ml equal to 0, and ms equals to minus half. So we have these two electrons, and you can observe that n, l, ml values are same for these two electrons, but ms value is different. For the first electron it has a plus half value, and the next one electron is a minus half value. So here ms value is different, so Pauli's exclusion principle is obeyed, and you cannot have another possibilities of this n, l, ml, ms value set. So only two possible states are there. So you can have only two electrons in the first orbit. Now let's study the Pauli's exclusion principle for n equals to 2. Now in this case, whenever we have n equal to 2, we have the two values of l. For n equal to 2, the values of l will be 0 and 1, by considering the restriction on the values of l that we have already learned. Then ml will have, you can observe that here for the first electron n has a value 2 and l has a value 0. So ml will have value 0 and ms will have a value plus half. For the second electron n is a 2, l is a 0, ml is also 0. For l equal to 0, ml has only one value 0, and ms always has a two value, plus half and minus half. So ms here will be for the second electron is minus half. So you can observe that these two first electrons are differ in the values of ms only. N is the same, l is the same, n is a 2 2, l is a 0 0, ml is a 0 0, and ms is a plus half and minus half. Now next value of l is 1. So you can observe that for the third electron l value is 1. Now corresponding to l equal to 1, we have three values of ml, namely minus 1, 0, and plus 1. So l equal to 1, and if you consider ml equal to minus 1, then ms again have two values, plus half and minus half. So electron number 3 has a value of ms as a plus half, and value of ms for electron number 4 is minus half, as shown here. So you can observe that for ml equals to minus 1, we have two values of ms, plus half and minus half. Similarly for ml equal to 0, because ml have three values for l equal to 1, minus 1, 0, and 1. For ml equal to 0, again we have two values of ms, plus half and minus half. Similarly for ml equal to 1, we have two values of ms as a plus half and minus half. So total you can observe that the two electrons have a value l equal to 0, ml equal to 0, and 6 electrons has a value l equal to 1, because for l equal to 1, 2 into 2l plus 1 that we have seen here, this case for given n value there can be only 2 into 2l plus 1 electrons. So here if you put l equal to 1, we will have 6 electrons. So here you can observe that for l equal to 1, there are 6 electrons which has a value l equal to 1, and corresponding values of ml are minus 1, 0, and plus 1. For each value of ml, there are two electrons which have a different ms, that is plus half and minus half. So we will have a total 6 electrons for l equal to 1, and each 6 electrons here have a different value of l, ml, and ms, and the total number of electrons in n equal to 2 are 8. And you can observe from this table that every electron has at least one different value for the set of quantum numbers of these 4 n, l, ml, and ms quantum numbers. So you can observe that all these 8 electrons, at least one value is different, either ml or ms, and you cannot have any other possible combination of this n, l, ml, and ms rather than this shown here. So there are only 8 electrons can be fitted in n equal to 2 states. There are no more than 8 electrons can be fitted in n equal to 2 state. Now let's move to the another topic, which is electronic configuration. Now electronic configuration of atom, whenever you write the electronic configuration of atom, it indicates the distribution of electrons in various shells or subshells. So electronic configuration of the atom is nothing but the distribution of the electrons in various shells and subshells. The shells of the electrons are represented by the letter KL, capital K, L, M, N, O, P, etc. And these letters are corresponding to n equals to 1, 2, 3, 4, 5, 6, 7 respectively. So for n equal to 1 we have a K shell, n equal to 2 we have a L shell, n equal to 3 we have a M shell, and so on. Now shells are further divided into subshells by the orbital quantum number small l, and these are denoted by the letters S, P, D, F, G, H, and go on. Here S stands for sharp, P stands for principal, D stands for diffuse, F stands for fundamental. These are the historical names, and so this corresponds to L equal to 0, 1, 2, 3 respectively. So for L equal to 0, whenever we say L equal to 0, it shows us the S subshell or S orbital. L equal to 1 gives us a P orbital, L equal to 2 gives us a D orbital, and L equal to 4 gives us a F orbital, L equal to 3 gives us a F orbital, L equal to 4 gives us a G orbital. And so these subshells are denoted by the letter SPDF, and shells are denoted by the letter KLMN, which are corresponding to n numbers. Now here you can observe that for the level K, we have a level and sub-level or shells or subshells. So for shells K, n value is 1. Now for n value 1, we have L value 0, only one value of L is there. For n equal to 1, L should be 0. And this corresponds to 1s. Here 1 stands for n equal to 1 and S stands for L equal to 0, because n equal to 1 means K shell and L equal to 0 means S subshell. So 1s represent as the n value 1 and L value 0. And we already know that in a K shell there are 2 electrons. Actually here L equal to 0, if you put in this formula 2 into 2L plus 1, if you put L equal to 0, you will get 2. So there are 2 electrons in the S subshell. And total number of electrons in this level, K level or K shell, corresponding to n equal to 1 are 2n square, which gives us the 2. For a L level, that is a L shell means n equal to 2. So here for n equal to 2, we have n equal to 2, we have here L has a 2 values, 1 and 0. So L equal to 0 stands for S subshell and L equal to 1 stands for a P subshell. So L equal to 0 here will give us a sub-level notation as 2s. So here we have 2s represent here 2 as a n value and S as a L value, which is 0. And for L equal to 1 we have a P. So L equal to 1 means P sub-level, and so we will get 2P. 2 here represent n number of that level and P represent the L value of that sub-level or subshell. Now we already know that in a S level there are 2 electrons can be fitted because L equal to 0 here, and in a P level P stands for L equal to 1, so you will get 2 into 2 plus 1, that is 6. So in 2p level there are 6 electrons and total there are 8 electrons in this L level, that is n equal to 2. In the M shell, that is n equal to 3, we have 3 values of L which are 0, 1 and 2. So this gives me a 3s sublevel, 3p sublevel and 3d sublevel. Here S stands for L equal to 0, P stands for L equal to 1 and D stands for L equal to 2. So in this case, in the 3s level again we have 2 electrons, in the 3p sub level we have 6 electron, and in a 3D sublevel we have a 10 electrons, because for D L has a 2, L equal to 2, and therefore the number of electrons in sublevel will be 2 into 2 plus 1, according to this formula, 2 into 2L plus 1. Here if I put L equal to 2, I will get 5 into 2, that is a 10. So in 3D sublevel there are 10 electrons, and overall there are 2 plus 6 plus 10, that is 18 electrons in the M level. Similarly, in the N level, that is N equal to 4, we have 4 values of L, 0, 1, 2 and 3, and therefore I will get a sublevel notation as 4S, 4P, 4D and 4F. Here 4S means N equal to 4 and L equal to 0. 4P means L equal to 4 and N equal to 4 and L equal to 1. 4D means N equal to 4 and L equal to 3. 4F means N equal to 4 and L equal to 4. So here you can observe that in a 4S level there are 2 electrons, in a 4P level there are 6 electrons, in the 4D sublevel there are 10 electrons, and in the 4F sublevel there are 18 electrons, and overall there are 2 plus 6 plus 10 plus 18, that is 32 electrons in the N level, and they are distributed as shown in the table. Now let's study about the Hund's rule. This is an important rule in atomic physics, and it states that when an atom has an orbital of equal energy, so if you consider the orbital of equal energy, the order in which they are filled with electrons is such that a maximum number of electrons have an unpaired spin. So if you consider orbital of same energy, for example L equals to 1, now in L equal to 1 orbital there can be a 2 into 2L plus 1, that is a 6 electrons can be fitted for L equal to 1. So there are 6 electrons in L equal to 1, but they filled in such a manner that the maximum number of electrons will have an unpaired spin, that is they are not pairing. So they want to occupy a position, first independent position, that they want to reside in the orbital single by their own. So they do not want to pair first. So maximum number of electrons want to reside independently in that orbital. We will understand this when we see the example. Now according to by using this Pauli's exclusion principle and Hund's rule, we can write the electronic configuration as, for hydrogen atom we know that the atomic number is 1, so it has only 1 electron. In the hydrogen atom there is only 1 electron, and this electron enters in a 1s subshell. So first subshell for N equal to 1, L equal to 0, we have 1s subshell, and there can be 2 electrons in this 1s subshell, but we have here only 1 electron for hydrogen atom, so its electronic configuration will be 1s1. Here 1 denotes the level number, S denotes the sublevel, and 1 superscript indicates the number of electrons in that sublevel. So helium atom, if you consider, we have Z equal to 2, and these 2 electrons are now reside inside the 1s orbital, that is both the electrons, one electron has a spin up, ms equal to plus half, and another electron has a spin down, ms equal to minus half, and therefore we have the electronic configuration for helium atom as a 1s2. For the lithium atom, Z equal to 3, and now 3 electrons are there, but here you can observe that 1s subshell can contain only 2 electrons, so third electron is filled in another level, that is N equal to 2 and L equal to 1, which is indicated by the letter 2s. So 2 electrons are in the 1s sublevel, and the next 1 electron, which is the third electron, will be filled in a 2s sublevel. So the electronic configuration will be 1s2, 2s1. For beryllium atom we have Z equal to 4, and then we will have the electronic configuration as 1s2 and 2s2. For boron atom we have atomic number as 5, so there are 5 electrons in the boron atom, and these 5 electrons get distributed as such 1s2, 2s2. Now s orbital has only the capacity of 2 electron, so next last electron, which is the fifth electron, will be filled in a 2p sublevel, which corresponds to n equal to 2 and l equal to 1. So the electronic configuration will be 1s2, 2s2 and 2p1. For the carbon atom, we have a Z equal to 6, and so the number of electrons in the carbon atom are 6, and so we will have the electronic configuration as 1s2, 2s2 and 2p2. For the nitrogen atom, we have 7 electrons, its atomic number is 7, and so electronic configuration will be 1s2, 2s2 and 2p3, because p orbital can contain 6 electrons. So that's why third electron will also go in a p orbital, but all these 3 electrons will have a up spin, same spin state. So they want to reside, and they are unpaired, so they want to reside a single by themselves in that orbital according to Hund's rule. And for oxygen atom has 8 electrons, so electronic configuration will be 1s2, 2s2, 2p4. Now let's understand the Hund's rule by using this example more clearly. Here you can observe that we have for Z equal to 4, which is a barium atom, in the n equal to 1, that is a k level or k shell, we know that there is a one subshell which is a 1s. Here n equal to 1 and s stands for l equal to 0. So in this 1s subshell, we will have 2 electrons, and remaining 2 electrons will be filled in a 2s subshell. And there we have 2 electrons in the 2s subshell, and they are paired. Both the electrons here are paired. So electronic configuration is 1s2 and 2s2. And now for Z equal to 5, you can observe that for Z equal to 5, boron atom is there, and for boron atom, the 2 electrons will be in 1s state, 2 electrons will be in 2s state, and now this s has only capacity of 2, so the further fifth electron will go in a p sublevel, and which has a up spin. So its electronic configuration is 1s2, 2s2 and 2p1. Now here is a more important example of carbon, Z equal to 6. Here you can observe that the 2 electrons are in the 1s sublevel, the 2 electrons are in a 2s sublevel, and now remaining 2 electrons, they do not pair. You can observe that instead of pairing, they prefer to remain a single. So these remaining 2 electrons are distributed in a p orbital such that both the electrons have an unpaired spin. They are not pairing, they are remaining single here. So this is the Hund's rule. So the 6th electron do not want to pair with the 5th electron. Instead of that, it prefer to remain a single, that is unpaired here. So, and therefore we will have here the electronic configuration as 1s2, 2s2 and 2p2. Again for Z equal to 7, that is a nitrogen atom, we have 2 electrons in a 1s level, 2 electrons in a 2s level, and the remaining 3 electrons, they occupy the 2p orbital unpaired, by remaining unpaired. Okay, and there, this is the Hund's rule. This is a consequence of the Hund's rule. So the filling of the electrons are as shown in the figure, and its electronic configuration is 1s2, 2s2 and 2p3. Similarly for Z equal to 8, that is oxygen atom, we have 2 electron in a 1s sublevel, 2 electron in a 2s sublevel, remaining 4 electrons, the 3 electrons remain unpaired. Now 4th electron do not have any other choice, so it pairs with the first electron, and there it forms a pair. And so now here we have only maximum 2 unpaired electrons in Z equal to 8. For Z equal to 9, that is a fluorine atom, we have 2 electrons in the 1s state, 2 electrons in the 2s state, and remaining 5 electrons filled in a p level, p sublevel. Now here you can observe that 2 pairs in the p level, p sublevel, and 1 electron is unpaired. So this is also the consequence of Hund's rule. So electronic configuration is written by under the application of Hund's rule and Pauli's exclusion principle. So according to Pauli's exclusion principle, all the electrons in an atom should have a different, either at least of the value of n, l, m, l, ms. Out of these 4 quantum number, at least one quantum number should be different for each electron. And according to Hund's rule, if you have an atom with equal orbital of, if you have an orbital of equal energy in an atom, then the order in which the electrons are filled in that orbital is such that the maximum number of electrons want to remain unpaired. So by obeying this condition, the electronic configuration is written. Now let's study how to write the quantum state of an electron. Now quantum state of, we have to write the quantum state of electron means we have to write the values of these 4 quantum number n, l, m, l and ms, and the set of values of these 4 quantum numbers will specify the quantum state of an electron. The values, the set of quantum numbers, this n, l, m, l and ms, this set of quantum numbers will give us the state of an electron, which is called as the quantum state of an electron. Now let us illustrate this concept of quantum state of electron by considering the example of oxygen atom as shown here. We know that for oxygen atom the atomic number is 8, and therefore there are 8 electrons in the oxygen atom. First 2 electron, as we have just seen, enters in a 1s sublevel. Here for oxygen atom you can observe that first 2 electrons are in a 1s sublevel. So for 1s sublevel, n is 1, s means l is equal to 0, ml is 0 and ms is plus half. For second electron, the set of quantum numbers will be like this: n equal to 1, l equal to 0, ml equal to 0 and ms equals to minus half. So this is the quantum state of second electron. Now third electron, you can observe here that third electron enters in a 2s subshell, and also fourth electron is also in 2s subshell. So for the third electron, we have n equal to 2, l equal to 0, ml equal to 0 and ms equal to plus half, because the third electron is in the 2s sublevel. So n is 2, l is 0, ml is 0 and ms is half. Fourth electron is also in 2s sublevel, but here now ms is minus half only. So this is the fourth electron's quantum state. N is 2, l is 0, ml is 0 and ms is minus half. So there exist 2 quantum states for 2s sublevel. Also there exist 2 quantum states for 1s sublevel corresponding to each electron. Now the remaining 4 electrons enters in a 2p sublevel. So here you can observe that for oxygen atom the 4 electrons are in a 2p sublevel. So here the first electron enter in a p level, which has a quantum state as follow. So quantum state of the fifth electron is n equal to 2, l equal to 1, ml equal to minus 1, ms equal to plus half. Sixth number's electron will be this. Here you can observe that the sixth number of electrons will be unpaired electron. The sixth electron, which is unpaired. Seventh electron is also unpaired. Eighth electron gets paired. So sixth and seventh electrons are unpaired. Sixth electron will have a quantum state as n equal to 2, l equal to 1. Now here ml has a value of 0 and ms has a value of plus half. So both fifth and sixth electron has a same spin state, up and up. Seventh electron is also has a up spin state, but the 8th electron paired with the 5th electron as shown here. The 8th electron, number 8 electron paired with the 5th electron, and it has a down state which is ms, which is corresponding to ms equals to minus half. So for 8th electron we have n equal to 2, l equal to 1, ml equal to minus 1 and ms equals to minus half, which indicates it has a spin down state. And so these are the quantum states of all electrons in the oxygen atom. So in this way you can write the quantum state of an electron. Simply you have to write the set of values of these 4 quantum numbers n, l, ml and ms, and that will indicate you the quantum state of an electron. So in 2p sublevel, now here 2p sublevel, in the p orbital there are 6 electrons actually, but in the case of oxygen, we are remained with only 4 electrons, because 4 electrons are already occupied by 1s and 2s sublevel. Remaining 4 electrons enters in a 2p level, but the two places are empty here because we only have 4 electrons, and so 2p orbital is not completely filled in the case of oxygen. This is about today's lecture. Now students have to solve following assignment. So students have to write the electronic configuration for chlorine atom. Now for chlorine atom, atomic number is 17. Here you can write the electronic configuration as we have written for another atoms as in this lecture. And also students have to write the quantum state of valence electron in sodium atom. So sodium atom has 11 electrons. The 11th electron is a valence electron, and you have to write the quantum state of that 11th electron. That is, you have to write the values of N, L, Ml and Ms quantum number for that 11th electron, which is a valence electron in sodium atom. Now let me summarize shortly what we have learned in this lecture. We have first studied about the Pauli's exclusion principle, which states that the no two electrons in an atom can have a same set of all 4 quantum numbers, which are N, L, Ml and Ms. For the given principal quantum number N, there are a maximum of 2n square electrons in that orbit. For the given value of L, there can be only 2 into 2L plus 1 electrons. For given value of L, that is, in a given subshell, there are only 2 into 2L plus 1 electrons. And the electronic configuration of the atom means the distribution of electrons in various levels or shells and subshells around the nucleus of the atoms. Also, we have learned about the Hund's rule, which states that when an atom has an orbital of equal energy, the order in which they are filled with electron is such that the maximum number of electrons remains unpaired. That is, they have unpaired spin. And we know that every electron in an atom has its own unique set of 4 quantum numbers N, L, Ml and Ms, and this set of quantum numbers specify the quantum state of an electron. In the upcoming lecture, we will study about how to write the spectral notation of quantum states, and we will take some examples. So this is about today's lecture. Thank you.